Okay, thanks for being here. It's really nice to be able to talk in the Nerd Nite. I will give a small introduction first. So I'm a statistician. I don't know what you guys think a statistician do. So I can give you more or less how it goes. In stats, we are most worried about probabilities, and you start studying statistics, and then you start to think you are getting good with probabilities, and then you start saying, okay, maybe I can make my living out of a casino, and I'm really on top of it. And, then you realize it's not working, and then you say, okay, I can at least try to stay there very long and drink my money worthy, and then you really learn the stats, and you realize that the casino has an edge on you, and you're never going to make it. It's never going to work. So that's what statisticians do sometimes. We are not necessarily data analysts. Statisticians, we play probabilities. And we like to be around tough problems. So when I finished my PhD, it was in something called Markov chain Monte Carlo. So Markov, a guy in Russia, he was running a warehouse, something like that, aligning orders. Tough problem. And Monte Carlo because, okay, yeah, I guess one of the first jobs of statisticians was helping gamblers to play cards, win. No, also statisticians used to be involved with lawyers. Bernoulli brothers, I don't know if anybody know Bernoulli probability. They were lawyers, so then how this connects to plants and food. I mean, you have hardcore gamblers and guys that like gambling and stuff like this working for. Also, statisticians are very well employed in the politics. We like to calculate probability of people winning elections. People also say damn lies in statistics. I don't know if you guys heard that one. Sometimes you can get a bad name. But you know, those guys in the plant business, they have a tough problem. So, and because, I mean, we are attracted by that kind of things. So that's a place where we flock. And I have to show you a little movie, and it's not necessarily with any corporate agenda to it, but I would like to give you an intro, and then we go into the core business. So,
lovely assistant.
My lovely assistant will play it because we are not very handy with computers either. We're good at with integrals.
By 20.
I can also do without it.
By 2050, nearly
just watch out.
People are living on planet Earth. What's more, our climate changes and available agricultural land decreases. How can we ensure that everyone has access to healthy and varied vegetables? Well, sometimes one of the solutions to these challenges is smaller than you think. It all starts with the right seeds for the right part of the world. In other words, vegetable breeding. The development of new varieties by combining characteristics of two plants into one new one. Our local subsidiaries around the world ensure that we know which improvements new varieties require to grow in that specific climate, and what the wishes and needs of the local customers are. Then our breeders set to work, focusing especially on great taste, on how well the new variety produces, and how well it resists diseases, plagues, or heat. We select the best plants and breed by crossing plants by hand. For this, we select two plants with the required characteristics. Then, we pollinate the pistil of one plant with the pollen of the other. The results are seeds of the crossing. The process is repeated until there's a winner. The development takes 7 to 10 years. But our innovative techniques help us to speed it up. The first leaves of a young plant can already be tested in the lab for the required combined characteristics. That shortens the process with years, as we don't need fully grown plants. Once we have an overall winner, seed is being produced worldwide. Then, the seed returns to NSSR, where it is processed, tested on quality, packed and shipped to over 110 countries. The results: increased production of quality vegetables, strong crops, needing less plant protection products and more sustainable agriculture. This way, we grow people all over the world have access to healthy and varied vegetables.
So, some things to mention. Enzazaden, that's a Dutch company. It's a family company. We are not dealing with transgenics or genetically modified organisms. That is a line of business of our competitors, which maybe some of them maybe you know or not. Companies like Bayer or Monsanto, and those guys, they are very big, and they do this kind of things. Of course, we are a company, but we are trying to do it in a way that is, agriculture is not normal. You cannot have 100 square meters of plants, the same species in one area. It's not natural, this, but at least we try to make it in a, let's say, not so aggressive way. But how do we do this? Well, this is all the types of, I believe, tomatoes, several types of tomatoes you could have. And yeah, there is a domestication. And during the domestication, you get many different types. And it is probably due to how those things being traveled all over the world. But you can have very strange looking creatures. And those things, we need to cross them. That's what you saw in the movie. We need to cross them. We need to find what to cross them. You need to put them together. And you need to find a way to select. Because we are not really able to go in and just modify one gene or put one gene. We are not really doing what is called genetic modification. So we have to do it taking many, many generations. But we like to do it in a way that is, we like to speed, because if you imagine that you are taking even 3 years to make a product, and in 3 years a lot of things can change. So we cannot just make a small mistake. It has to be very certain. And in the past, when you make a product in 7 years, it was even worse, because in 7 years, by the time you get to that product, maybe the market is completely different. So we need to go fast. And the type of genetic variation that you can get in terms of vegetables, of course, is much more than what you see in the Albert Heijn or in the supermarket. This is corn, peppers, I think, cucumbers. I work with plants, but I'm not really a plant breeder. Once I tried one of those peppers, I think I had a hippo for many, many hours. I had to drink milk. It was enormously powerful. Spicy, the thing is because they need to, sometimes they keep those peppers in kind of what they call a gene bank. Because sometimes we have some viruses and they kind of evolve and then they break resistance, so you have to go back and make the thing again. Then they need to restore the old source. Then they need to go back sometimes to some of those weird looking peppers to do all over again, the whole thing. And then those things, I don't think peppers were meant to be eaten in the beginning, but somehow we managed to make it. So now, without getting too technical, so what the situation is that we have a lot of these different plants. They have been modified because people have selected them. And then what really happens here is that they increase the frequency of some genes. And then by increasing the frequency of some genes, they lead to different things. And then what we do then, we take this genetic variation and we start crossing them. And with some biotechnology tools, we just look what is inside the DNA of the plant and we make some crosses that are designed. Very simple thing. We take 2 plants, we cross and we have a hybrid, and then that's a cross. Now, we start with 2 parents. With plants, we can do some things that can be really intriguing. Like if I'm a plant, I can cross myself to myself, and I can do this for many generations until I'm pure me. See, That kind of thing can happen with plants. That's how you get a P1 that is pure. So if I kind of have a kid of myself for like 8 times, then finally I'm just identical to myself. So I'm become what they call the pure line or homozygous. Now if I cross myself with somebody that has do the same, then you make what we call an F1. One guy, an old guy, very long time ago was playing with this kind of thing. His name was Mendel. So that's kind of the business he was doing with peas. And when you cross the thing back, then you start splitting the pieces of yourself and your partner through the whole offsprings. That is this then will be an F2 population. And then that thing, we just completely check every single DNA base pair and we check everything that is there, not there, those little pieces. That's the way it used to be. And okay, if you can just take this little piece here off and put another piece, you can speed the thing up. But if you cannot, you have to continue. And the thing goes, and then you keep crossing until you finally have a population that everybody, I am again myself, but I get a little bit piece from somebody else. That is this guy here. And then when I was myself, pure me, and let's say, for example, I had, I'm just like this. Then when I get that little piece here, I develop an extra arm. That little piece is responsible for the extra arm. If I do this thousands of times, then I know, okay, yeah, that's the gene for the extra arm. Then, you can run a patent on it, or then I have copyrights. Not me, people who made it. Huh? And if you put that gene there from another species that makes a plant resist to agrotoxics, for example, then you have a transgenic. Then you can then you have a completely different business model, and I don't want to talk about it. But this is what is happening. So this is what is called recombinant inbred lines. So like if you go on doing this is our core business. We do this, and then those populations you can save, you can store, you can save the seeds, you can freeze them, you can keep it in stock, you can make them again if you want. You can play with it, you can do many different characters, we can ship all over the world and then find out what it is, and that's why it takes 7 to 3 years to make a product. Now, there is a little problem here. It's that when we get to this level, and then we convert this into a data set, let's say in an Excel file, what would happen is that we would have, let's say, a few hundreds of families of, let's say, recombinant inbred lines. And the pieces that are different is not going to be just one. They're going to be what we call genome-wide. So it can lead to a situation that you have 300 rows in Excel and like 17 million columns in a file. And then, we have to kind of try to check what is causing that effect. Like, if you go back, what was the piece that caused that hybrid to be so much bigger than their parents, you see? Because this is just an article from Nature magazine. This is just one piece of the DNA causing an enormous amount of extra growth in the plant, extra tomatoes. So we need to find where that little piece is, yeah? Then you get to, and that is when the statisticians come in, right? Because then they're addicted to this kind of stuff. We like games, huh? Then we're like, oh man, that's fun. Now we need to find the combinations. So we need to test them. Yeah? So the problem is that when you are going, if you know a little bit about combinations, when you test them one by one, now that's easy. That's no problem. I mean, you can put 15 million columns in you can do a for loop on it, and it's very simple. But if you try to make combinations of it, then things get very not so nice very quickly. Here is just 3, 4 cases. Then if you have 4 genes, you can make more or less 15 models if you want to test them all. And of course, the statisticians, we don't like this so much. We will, in statistical language, we say we run out of degrees of freedom. We don't have enough sample size. But yeah, this sample size is what it is. You should try to look for it. Then they'll say, man, but if you were a good statistician, you will find it, So, and you have to do it with what you have. Now, what finally happens is that if you would assume that we are making 10,000 models per second, and if you insist on going back here, if you go back to this, and you say that K here is the number of, if you would just say, K, I just want to make models of size 2, size 3, size 4. So instead of, let's say that we would just not make the models of size 4 and size 3, so you just have K equals to 2. So in that case, you skip 5 models, so you'd make still 10 models. Huh? So you say, okay, we are not going to be very greedy. You will skip the more complex models, and we will just test 2 by 2s, bivariate correlations. We skip the 3 ones. Yeah? So you have K equals to 2. Yeah, but in here we have the log scale. So it's like, for example, if you would have, let's say in the example that I say, if you have, if you start this thing with 15, let's say 15 million variables, you'll be easily in the log 10 above, easily. Log 5 is around 1,000 or so. So, yeah, if you would, let's say, just have 1,000 variables and you want to consider all models of size 10, and you are doing 10,000 models per second, you can, the amount of times it takes to compute all the potential problems is something that we cannot make it. We cannot wait those thousands of years to do it. It's not going to work out. This is impossible. So if I have 15 million variables and I want to evaluate all models, it's not going to work out because I'm going to be dead by the time the thing is finished running. So we have a little problem. We cannot evaluate all models. So we have a huge blind spot. So we need to find some tricks how to do it. Because if there is a model that is good and I didn't test it, I don't know it. And if there is a potential genetic combination that can lead to increase of food, let's be clear, it makes us the ability to sell seeds. So we should test it. But the reality is that we're really not testing. Hopefully, there are some new tools, deep learning. Maybe the new generation can come with some more sophisticated stuff and figure out ways. But the reality is the problem is intractable to do it strictly, to do it really precise. So what actually we do, we hope for the best, try to do what we can, try to do some GPUs, we try to make some simplifications, we try to get some Bayesian statistics. I don't know if people know about Bayesian statistics. It's a different flavor of statistics. We use priors, and some people don't like it so much, but we do use priors. Then we say this and this combination is never going to make it, so it's out. We start making heuristics, because we have to solve this. Now, once you are done and you have the model, well, there is another problem. So mathematics, that is also not so nice, because mathematicians, they are different than statisticians. Huh? The mathematicians, they want proofs of things. Huh? We are more flexible. For us, we just like the thing to work, Don't have to, it's a bit more simple. We don't have to take so much calculus or stuff. We are much more flexible. But when you have to put that thing together, then there is another problem, because if you remember my slides before, once we know the piece of the DNA that is good, what can happen is that maybe there is a piece that is back in one type of plant that I need to cross to bring it together. And then bringing this thing together can take a lot amount of plants to do. And this is something really from my competitors. This is from Bayer. They have put up a whole publication about this. And of course, there is a little competition now that if you have enough computer power, we should be able to know how to combine the plants. And let me try to explain how this thing works. This is really, I'm going to try to venture into this. It's not really my area of super expertise, but some mathematicians that we work with, they tell us that breed is an NP-hard problem. And then I'm going to be brief on this one, try to explain how it is. But apparently something like a Sudoku is an NP problem that you can solve it and you can prove that you get to the right solution. And as the board gets bigger, it gets harder to prove that the solution is right. Apparently, there are problems that it's very hard to prove that you have the right solution. And those are the NP hard ones. Travel salesman problem is one of these kind of things. And crossing a plant to put the right combination of genes together, apparently, according to the mathematical center here in Amsterdam, is one kind of problems like this. So once I find that to make my ideal plant, I need to make this combination in the genome, so I need all of these positions to be one. And if I have to start from that thing, there could be in many, many ways to get to this point, and it's going to be very hard for me to prove that this is the best solution, because there could be many other ways that I could get to this. And so this is a crossing schedule. I don't know how many of you have seen a crossing schedule. I don't think, actually, to be honest with you, the first time I was invited to give a talk here, I was a little bit shocked, because we were just in West Friesland in our company, and then a lady said, "Why don't you give a talk in the Nerd Nite?" And we're like, "What?" We are in agriculture. We are the seed industry. We're not giving too much talks. But okay, then I think it was a good idea. So I don't think too many people have seen how this works, but our initial plants, our initial blocks there could be equivalent to one of those tomatoes you saw in the first drawing. And what we know, because we know the genes that cause the trait of interest, the characteristics that we want, we know where they are in our pool. So I know, for example, that if I cross that first plant with that first plant, if I have 209 kids of that first cross, I have a 90% chance of finding that one amongst the whole population. So once I find this, and if I take that first one there, and if I cross that one back to itself, 29 times, I have 90% chance of finding that thing. And you keep crossing this thing using all those plants until you get to here. And in your final step, you have used 1,367 plants. Now, if it's costing you, let's say, 500 euros for a plant, then you have the cost of this. And if it's taking you, if you are in an unfortunate position, for example, that you work with oil palm, each one of those little arrows is costing you 7 years. So by the time you are here, you are already talking about 7, 14, 21. You are 28 years down the line, and before you finish your thing, you should already be ready for retirement. So it can be a situation like this. There can be plants, the generations can be a long time. Huh? So it's a combination of problems. You need to find the right thing, and you need to put the thing together. And that makes the thing very tricky. And then, of course, then if you do biotech, you can shorten this thing up. But yeah, should we do genetic modification or not? That's a discussion maybe for another Nerd Nite, not for mine. I'm more interested in stats. But you can see you have discussion and have a lot of discussion about this. So this is an example that, for example, you have two schemes. You want to arrive at this combination. So you start from this pool. So some of those things there are some of these plants. You cross them. Then you have an option B that is way cheaper than an option A. And then we literally have computers going on calculating these options for us and looking, because the space of possibilities are enormous. And also we have the things looking to find out the genes first and then how to combine it. And all of this is just an in silico process, all in computers, 24/7, non-stop. That's what the seed business is doing at this moment. I can tell you, there are computers somewhere in some seed company that is looking for how to find genes, how to combine them. So, given all of this, and how are we doing? So it's a matter of questioning, okay, in terms of food production, how is the status? So the current situation is that, okay, yeah, we have a challenge that by 2050, this is the latest report from these trends in plant science, that's pretty recent, and given a lot of technology that we have, we should be in average, we should improve the gain of the genetics, so we should be able to find 2% better genes to improve the plants overall, 2% a year, if we want to be in 2050 at the level of fruit production that you have to be in order to make sure that it's not really a kind of Game of Thrones kind of scenario that is really bad. And we are managing from 0.8 to 1.2 at this moment. So it's, of course, you don't notice it immediately, but it goes a little bit behind every time. I don't want to end up with a sad note, but I also don't want to end up with something that is not accurate. Well, this is the Nerd Nite, right? But we are going to try our ultimate best to make this. We are trying this all over the world. We are trying to improve this. And yeah, I think with the improvement of technology, we will be able to crack those things down. I think there will be new technologies coming around. There is an artificial intelligence story going on, deep learning, new technologies to speed the whole thing. I think we will catch up. But we need to speed up. And then that's also a little bit why I accept to come here and have a talk this with you guys, to expose the situation. So that's it.